Hello, this is Dr. Jason Harrington, and today we'll be talking about electrical circuits. A couple things. We have two laws, and they basically just tell us which one we want to solve for. Kirchhoff's current law says the algebraic sum of current flowing into any junction point must be zero. And then Kirchhoff's voltage law says the algebraic sum of the instantaneous in potential or voltage drops around any closed loop must be zero. So just for some notation here, the current in a circuit after a switch, that's just I. And then the charge of a capacitor is Q of t. And you'll notice his relationship between I and the derivative of Q. Then we have three different types that we're going to be using just in this class. We have inductance, resistance, and capacitance. And these are all going to be constants. So let's go ahead and start show you what these things actually are. So our first electrical component is a resistor. And according to Ohm's law, the voltage drop E sub R across the resistor is proportional to the current I passing through the resistor. So when you're looking at a schematic and you see this jaggedy line that you have here within the circuit goes up and down, that's typically a resistor. And what that's, the basic idea, I don't want to oversimplify everything, but okay, now if you want to be able to read a resistor, and again, you don't have to do this. I don't want to panic anybody. People may start panicking, but so again, nowhere in this class am I ever going to ask you to read a resistor, but just to give you an idea of how to read them real quick. This one is actually kind of backwards. This gold band should be on the right, so it's kind of flipped around. So if you look at the colors, I have brown in the first band, black in the second, and then I have black in the third, and then gold last. So in the first one, this is a 1. So I have 1, this one is a 0, and then this third one basically tells us what to multiply it by. So it can be multiplied by 1,000 or, some other number, 1,000, 100. But in this case, this is just multiplied literally by 1, which is just 10 to the 0. And the gold is our tolerance. This is going to have a 5% tolerance. All right, and if there isn't a gold band, that typically means it's up to like 20% tolerance or so. And so this resistor here is going to be 10 ohm resistor. And so typically the people who created these laws get to actually create the units. So in this case, resistors are always going to be in terms of ohm. Now, according to Faraday's law and Lenz's law, the voltage drop E sub L across an inductor is proportional to the instantaneous rate of change to the current I. Now, what's neat about this is with this being in the schematic, you can almost see where it comes from over here. Basically, you have a wire, it's going around it several times, and then it comes back down. These used to be used a lot in radios, not so much anymore, but now they're used to like clean up signals because it kind of absorbs a lot of that extraneous stuff going on. So for example, if you use cable, then you might have one of these at the end of the cable, at the cable line, so that if there's just too much static, you'll kind of just let that go away. Now in this case, what we have is E sub L is going to be equal to either L di over dt or L of the second derivative of the voltage drop. And typically what you use is you use H for Henry. So typically it's H, that's for Henry's, and that's typically what the units will be when we talk about this. So the voltage drop E sub C across a capacitor is proportional to the electric charge Q on the capacitor. And this is what it's going to look like on a schematic. Basically, the concept of this one is it's going to hold a charge. And over here, when you look at the examples that I have, you see that typically it's just written on the side. Now in this class, you'll want to put everything in terms of farad. So our units in this course will be the farad. But you'll notice here when you see this mu farad, that just means microfarad. So typically, most of us will actually just see microfarad. And that just means you have to multiply through by constants to turn it over. It's not that difficult. And the equation for this is E sub c is equal to 1 over c cubed. Now again, please don't panic. You're not going to be in charge of or held responsible for reading these things. What I will be giving you is I will give you the capacitance, the resistor, or the inductor information already, and then you just have to be able to solve the ODE. So now this is an example of a circuit diagram. And the way you would read this is you would say E sub L plus E sub R. So if I go around, that should be exactly equal to the energy source that I have, the power source. So over here I have the power source. And sometimes it's either on or off, which is pretty simple. But oftentimes you'll see things where it's maybe sinusoidal or going up and down. Maybe there's some frequency to it. And when I convert this over to a difference equation, the E sub L, I can just remember, is going to be, let's see, that's just going to be L times the derivative, the second derivative of Q with respect to T squared plus the resistor R dQ over dt is equal to some function. And if you make a note here, note that dq over dt is just equal to I, right? Where we have I as the actual current, and typically, I should write this out, the current is typically in amps. Okay, so now, if I write in terms of this, that's the same thing as saying L times di divided by dt plus Ri is equal to some electrical energy source. And this is actually, you're going to learn how to solve this later on. That's going to happen next week or so. This you can solve now. And so a lot of times they'll give that in terms of current or in amps. And remember, these are just constants. You know, those are just constants. So you have a linear function with just constants. It's pretty easy to solve. And again, this would just be an LR circuit, meaning it just has an inductor and a resistor. All right, now over here we have an RC circuit. And what that means is, of course, by Kirchhoff's laws, we have E sub R plus E sub C is just equal to E of T. And so you kind of see a pattern to this. Basically what you're going to do is you add up everything that you do as you go around, very simply in a simple circuit, and then that must equal the voltage source. And the voltage, of course, can be oscillating or be constant on or off or any one of those things. So now I just have to convert this into a differential equation. So the E sub R, that's just going to turn into R times dQ over dt plus 1 over C Q equals E sub T. And again, this one is nice and linear, so you'll probably see something of this example here as we talk about it. Now let's actually start to do an example. Okay, so for this one we say we have a 100-volt electromotive force that is applied to an RC series circuit in which the resistance is 200 ohms and the capacitance is 10 to the negative 4 farad. Then it says find the charge, Q of T, on the capacitor if the initial condition is 0, and then find the current. So there's a lot of things going on here. So let's write all this out. Now if I were to make the little circuit, you don't have to, again I'm very visual so I like to see it. I would have my energy source would go up. I would have some resistor here, go down, and then I would have a capacitor going back in there. That's probably a terrible looking illustration, but that's what I have. Now I know that the R is given to me as 200 ohms, and I also know that the capacitance is given to me as 10 to the negative 4 farad. And then I also know that E of t is 100. So E of t is just a constant, 100. So if I write this out, this says E sub r plus E sub c is equal to E of t. And when I make my substitution, this is going to be r times dq over dt plus 1 over c times q is equal to E of t. And so now I just have to make my substitutions for the constants here. These two are just constant, and believe it or not, what's really nice about this first example here is that the voltage, the electromotive force is actually also constant. So if I make my substitutions here, I'm going to have R is 200. So I have 200 dq over dt plus 1 over 10 to the negative 4 times q. And that's equal to 100. Now this is a nice linear ODE. Let's see what happens when I just divide everything through by 200. Then I end up getting dq over dt plus, that's just going to be 500, because don't forget that 10 to the negative 4 goes on top, and then you divide that by 200. That's going to be q, and then 100 divided by 200 is just 1/2. And so this is our actually ODE to solve, which is pretty nice and easy. So if I try to solve this, I'm going to have dq over dt plus 50q is equal to 1/2. So I need an integrating factor. So I'm going to have my int factor, because it's linear. I'm going to have mu of t, I almost put x. Got to be careful, this one's t. E to the integral of 50 dt, which is equal to e to the 50t. So now when I multiply each one of these guys by that, I have dq over dt times e to the 50t plus 50e to the 50t times q is equal to 1/2 e to the 50t. And then you can see that right here, that should turn into d over dt times, let's see, e to the 50t times q. And again, please make sure that you check this to see if it works, at least in your head. You would say the first times the derivative of the second, okay, that's there, plus the second times the derivative of the first, okay, that's there. Now, that's going to equal to 1/2 e to the 50t. Now what I'm going to do is integrate both sides. So we have e to the 50t times q is equal to the integral of 1/2 e to the 50t dt, and that's a pretty nice little integral there. That's just going to be 1 over 100 e to the 50t, and that's where my constant is going to come. Then I simply divide everything through by e to the 50t. So that means that q of t is going to be equal to 1 over 100 plus c times e to the negative 50t. And recall that q of 0, it was equal to 0. And so note that q of 0 was equal to 0. So that means that I'm just going to have to put in negative 100 in front of this. So I have q of t is equal to 1 over 100 minus 1 over 100 e to the negative 50t. All right, so that's the first part of this. Now, if I want to find I in this case, so that was the first part. If I want to find I, then don't forget that I is equal to just the derivative of q with respect to t. So if I take the derivative of this thing, then that means that I of t is just going to be equal to the derivative. So the derivative of the first, well, that's just 0, and then here we can just use the chain rule. Bring the 50 down, that becomes positive. So we see that's just going to turn into 1/2 e to the negative 50t. So all I did there was just take the derivative, right? Take the derivative of that with respect to t to get I of t. And that's our answers for both of those. All right, cool. All right, so now in this example we have a circuit has a resistor, inductor, and voltage source. The resistor is 55 ohms, the inductance is 4 henries, and the voltage source is 320 cosine 5t after t seconds. Let I of t, or I of t, be the current in amp in the circuit after t seconds. Find the differential equation for the derivative of I of t, and now assume the initial condition is 0 goes to 0. And then you want to find the current after half a second, and you want to round this to, say, 2 decimal places. All right, now the first thing, again, I think typically a little bit more visually. So we have our energy source here, and then we'll have an inductor. And again, that's kind of loopy. Remember, it was wrapping around that piece that we saw in the picture. Well, not all of them. There's some that do it a little bit more discreetly. And then we also have, let's see, what else? Then we have a resistor. It's a bit more jaggedy. Okay, wow. Mine's becoming a little bit more. So we have our L is equal to 4, and then we have our resistance is equal to 55 ohms. Okay, now if I were to create the model for this, you would have E sub L plus E sub R is equal to your energy source, and that's with Kirchhoff's law. Now, E sub L we can just write down as L times d squared q over dt squared, the second derivative of q, plus R of dq over dt is equal to 320 cosine 5t. And then just like last time, we saw that note here that I is just equal to the derivative of q over dt. So that's going to turn into L times the derivative of I. So you can write that as I prime or di over dt plus R times I is equal to 320 cosine of 5t. Okay, now that's of course linear, so let's go ahead and work this one out. Well, before I do, let's put in all the numbers that we have. So we have 4 times di over dt plus our resistance, which is 55 I, is equal to 320 cosine of 5t. So that's our ODE. And that's the one I want to solve. Now it said first, I want to find the derivative of I just by itself. So the derivative of I, that's I prime is going to be equal to negative 55I plus 320 cosine of 5t divided by 4 in each one of these. And that's just 80. So, which, I hate not simplifying things when I write them down, but that'll just be 80. So when you do your homework, you'll see a question that may say, solve for R prime. And that's fine. You can just write it out just like what I have here at this line, and that'll be fine. But we need to actually solve the ODE, which is slightly different. So we have 4 di over dt plus 55i is equal to 320 cosine of 5t. Cool. Now in this case, again, I divide everything through by 4. So I have di, so I can figure out what the multiplicative factor is going to be, plus this is going to be 55 over 4. I is equal to 80 cosine of 5t. So that means that my integrating factor, mu of t, is going to be e to the 55 over 4 dt, which is really just going to be e to the 55 over 4t. Okay, so when I multiply that all through, then I should have, let's see, I should have di over dt times e to the 55 over 4t plus 55 over 4 times e to the 55 over 4t I, and that is equal to e to the 55 over 4 times 80, oh, t, don't forget the little t there, times cosine of 5t. All right. Now, what we have is, on the left-hand side, this should turn really nicely into d over dt of I times e to the 55 over 4t. And again, please check every once in a while. Just when you're taking a test, for example, you're like, did I do this right? If I have the first times the derivative of the second, okay, that's over here. And if I have the second times the derivative of the first, that's over here. So that does in fact work. And the right hand side becomes 80 e to the 55 over 4t cosine of 5t. Now when you integrate both sides of this, you get I times e to the 54 over 4 times t, and this one I went ahead and did, I did this ahead of time because that's not too bad. It's just integration by parts. So it's 704 times e to the 55 over 4 cosine of 5t divided by 137 plus, now I'm going to have 256 e to the 55 over 4 t sine of 5t, all divided by 137 plus c. And the cool thing is, check this out, bam, those things are going to go away in each one. I forgot a little t here. That's how I knew I made it. I forgot the little part. Bam, that goes away. Bam, that should go away as well. So now I have I of t is just going to be equal to 704 divided by 137 times cosine of 5t plus 256 divided by 137 times sine of 5t plus c times e to the negative 55 over 4t. Now to find c, you have to recall that I of 0 is equal to 0. Okay. Now we can actually just think about this really quickly. If I put 0 into this, this is just 704 divided by 137. If I put 0 into this term, I just get 0. If I put 0 in there, I get c. So if this whole thing is going to be 0 at 0, then that just has to be, this c is just the negative of this guy to cancel out. So I have I of t is going to be equal to 704 divided by 137 cosine of 5t plus 256 divided by 137 sine of 5t minus 704 divided by 137 e to the negative 55 over 4 t. So the last question just says, what is I of 0.5 seconds? What is going to be the amps in this case? And if I just put 0.5 into all these little terms here, I've already typed this in, and we only want 3 decimal digits of accuracy. Here's what I get. I get negative 3.003822467. That's all the digits I get out from my calculator. It still goes on forever, by the way. But what I would type in actually would be just, I'd look to see if I need to round here. And in this case, I don't. So it's really just going to be negative 3.00. And don't forget our units is going to be A, or ampere. I'll just write that down. Cool. And that answers that question. So basically this had 3 parts to it. First we had to solve for I prime to put it in our homework problem. The second thing we had to solve the I, solve what C was, and then the last question was to put in 0.5. Cool. I'll put out a video as well that will do an example of this in an actual real physical circuit. All right. Good luck.